No, sorry. So in this definition, we have this word unique that we're in.
Yeah.
And in this definition, the word unique appears
Yeah.
here as we open this up. Okay, so I've given this alternate explanation or definition of product to tie this back to the concept of terminal object that we just talked about yesterday. Also to give us some examples of weird categories that we can form, and examples of in category theory, but also maybe importantly, in category theory, like every concept can be turned into like every other concept. Obviously that's not true, but like it's all going true. Okay, so like you have the definition of product, the definition of terminal object, and then we can write the definition of product in terms of the definition of terminal object, and like vice versa. Like everything can be turned into everything else. Maybe the least limited thing in category theory, so obviously something that like a concept with some particular properties or behavior that kind of limit it from expressing everything else. But in the first textbook about category theory, Categories for the Working Mathematician by Summers DeClaine, that is invented category theory, or was one of the people who did that. There's an important chapter called All Concepts Are Con Extensions. So we won't talk about con extensions this week, but con extensions is like maybe the most general thing that really does encapsulate everything. Okay, are there any questions? Okay, so what do I want to do next? Okay, I want to give another alternate definition that feels important because it's kind of how when you start doing serious calculations about category theory, you're not going to use a definition like this. You're going to use a definition that I'm going to do in a second right now. So this is a good definition for like thinking about what's actually going on. There are these arrows, there are these objects. We induce this unique morphism. It's very concrete. So what I'm about to write down is very good for doing calculations and for proving things. Okay, so here's another definition. So I'm going to say that also proving that this is equivalent to the first two that I gave is also an exercise for you guys. So maybe it's a little bit harder. So maybe it requires some comfortability with category theory that maybe not everyone has gained in the past few days. Okay, so in another definition, consider, I called them A and B before. So consider A and B in the objects of some category. The product. Now, I hope someone will ask me a question or less complaint about what I'm about to write down, because it's slightly different than what I wrote over there. You will see. The product of A and B is an object with the property that, if I look at, so we completely forgot about this weird category that we just defined. It's a totally different thing. So are all happening in the original category C. So if I want to understand maps into A times B, so I want to calculate what this guy is from some arbitrary Z, then this is this is the product of maps from Z into A and maps from Z into B. Yes.
And that isomorphism is not an isomorphism in the basic category, it's an isomorphism in sets of morphisms.
Exactly. So these things are sets, okay? Or they could be types if you want to do everything in type theory. That's a good thing to do. So set theory, type theory, whatever your kind of your foundation. So if these are all sets or types, here we're taking the product of two sets which we talked about. Just a normal Cartesian product, and here I'm asking for a bijection between these sets, aka an isomorphism in the category of sets. I need to write some more words. Natural in Z. Okay, so unfortunately I don't know what natural in Z means yet, so just ignore that part. I need to write it so that I'm not lying to you. Okay, but let's think about this isomorphism real quick. So if we think about going from left to right, so we need a function that takes us from left to right. So if we start with a morphism like this, so if we actually start with the U sub Z, then the A times B is equipped with these two maps. So just by composing this guy with this guy, we get this map from Z to A. And similarly, we get a map from Z to B. So a map from Z to A times B induces these maps. So that's the morphism in this direction. And the morphism in this direction is what we said more explicitly here, which is that if you have a map to A from Z, and you have a map from Z to B, so if you have a pair in this product, then you get a unique morphism here that makes the triangles unique. Okay? So first thing is that you get a morphism here. Now I'm going to say something very quickly that maybe you should go back and think about later because it might be a lot for right now. So you first of all get a morphism here, that's a UZ. The fact that it makes the triangles commute so that if you then go back using the function over here, that's the identity. And the fact that it's unique gives you the other identity that you need. Because you might remember that like a bijection is something that has a unique fiber, something like that. Think about it before. Okay, so yeah, so this is a more advanced notion. And yeah, in particular, I will talk about neutrality later in this course, but you might want to find a friend who knows a little bit about category theory and what neutrality means, and you can try to prove that this definition is the same as the other ones. But let me give a simpler definition. Well, before I do that, let me talk a little bit more about this definition. The reason why I want to show this to you, as I said, is because like this is how you actually do it as a working category theory. But more important, or more like basically like the philosophy that is giving us the fact that this is a nice definition, is what I said before, which is that in category theory, we study objects via their relationships with the other objects, via the functions of the other objects. And this definition defines this object A times B in terms of what the Hom set from an arbitrary Z into A times B looks like. And if the object, such that morphisms into it, look like this. Okay, so we characterize A times B via these morphisms, which is also what's happening here because they're equivalent, but I'm going to do that. Yes?
I guess just wondering, in all of these definitions, the fact that A times B is in C, does that mean, I guess that sort of means that in any category we can create these products, or is it a special thing of some categories we can create these?
It's a special thing.
Okay.
So just like the terminal object,
Yeah.
it doesn't always exist.
Okay. Because the morphisms might not lie down.
Yeah. So for instance, like, let's think about the most basic example, which just doesn't work. So if we have a category before and it's totally disconnected like this, like if we had a product A times B, that should maybe be the same as either A or B, then it would have these two maps. So then the category would have to be connected. And it's definitely not connected without assuming this picture guy. So it doesn't have products. Yeah. So when I say like the product is the object such a blah blah blah, it just means if there is such an object, then it is the product. Yeah.
Which part of this definition is the part that corresponds to pi A?
Oh, yeah, that's a very good question. Okay, it's not coming up very explicitly, but there's a nice trick you should do. So whenever you see something like this, you should think about what happens when I put in the identity, and then something nice always comes out. So, okay, maybe putting the identity here is weird because the A and the B are usually different, so like, how do we make Z both A and B? Really different identity, I don't know. But over here, we can currently make Z A times B.
Right, okay.
And then we have some function going from here to here. And the definition just says there's some isomorphism going from here to here. So we can just plug in the identity, which is kind of a special morphism. And then we say, okay, now we get something, we don't know what it is, so we get some special morphism out on this side, or some special element out on this side, which is a morphism from B to A and a morphism from B to Z.
Right, okay.
Yeah, so this, like this is a lot of words. There are also words over there, but this is a lot of words, and this is like just one equation, basically. You might be able to imagine that this equational reasoning is sometimes easier than figuring out a bunch of words. So it really encapsulates a lot from this definition. Yeah.
So is the X under the hom set, ZA, does that mean anything?
That is times. So this set is equal to this set times this set.
Oh, okay, okay.
Yeah, thanks. I ran out of room. Okay, so now I want to give a definition in the same style of terminal object. And this one will be, I think, possible for everyone to show that it's equivalent to what I gave before. Actually, it's kind of obvious when I write it. So, terminal object, if it exists, is an object, call it T again, such that, so I'm going to write something in this style. So by this style, I mean that the thing on the left should be like coms, morphisms from an arbitrary guy into this guy. We're defining T. So com from Z to T. And then what follows is the characterization of the HOM set. It's giving us like how we study things in category theory via their interactions with the other objects. And who can tell me what should be on this side? Yes?
Singleton set.
Exactly, the singleton. So maybe I should write it like I did. Previous things, the singleton set. Okay, so let's just think about why this is true. I mean, this is almost exactly the same definition that I gave yesterday for terminal object. It was the collection of morphisms, the set of morphisms from an arbitrary Z to T to be the singleton. I want there to be exactly one morphism from any Z to T. Yes.
Is that the same as saying that the amount of morphisms from an arbitrary element to T has cardinality 1?
Yes, exactly. Yes. So we want it to be in bijection with our favorite set of cardinality 1, and that means that it has cardinality 1. Cardinality is defined in terms of bijection, so it means exactly that this set has cardinality 1. So writing this is exactly saying that there needs to be exactly one morphism from Z. Okay. So now let's also think about some nice things going on in these definitions. So for this one way to think about, or like, well, how I remember it actually, is that you can think about what's going on, moving from left to right, as pulling out the times sign. And so we have morphisms from Z into a product. And that's the same as the product of the morphisms into the separate things. Okay, so we're pulling out the Z somehow. Or sorry, we're pulling out the times somehow. And then the A and the B, of course, they have to split up. And here, we're going to go less obvious way, but hopefully it's clear by analogy. I also kind of want to pull out the terminal object, or the concept of being terminal or something. So maps from Z into the terminal object is a terminal object in set. Just like maps into a product is a product in set. That makes sense. You guys see the similarity? Okay. And so this is part of the statement that commas like this, where you take comma something, comma a terminal object or a product, which are instances of something called a limit, that this commutes with limits. So taking the hom of something and a limit, so you can take the limit out. And then you can take the product out and then take the concept of being terminal out. Yes?
So whenever we have isomorphism between two Hom sets, it really is sufficient to just say that they are the same size, like that they are the same personality.
Yeah, but often the function that goes between them might be important. So often you say like a particular function is an isomorphism. Here it's not going on, but that's often happening. Okay, so now what to do next? So next, let's talk quickly about concept of coproduct. So last time we talked about terminal objects and initial objects, and we talked about opposite categories and duality. So when we do something dual, we often add the prefix co, or take away co maybe, to denote the dual thing. So like the initial object is the co-terminal object, and the terminal object is the co-initial object. So we have these special words, initial and terminal, so we never really say what I just said. But for products, we definitely talk about co-products. So the co-product of two objects in a category C is, say, so it's a product of A and B in C opposite. So maybe I won't waste fresh ink in this marker by writing down the definition. You just like writing down the definition in this style. You just think about it real quick. Okay. So we need. Oh, maybe I should give you some notation. You usually write it with plus. Okay. So the co-product then of A and B is going to consist first of an object. Now we call it A plus B, not A times B. The first thing doesn't change because when we take the op of C, the objects don't change, okay? So the first part is the same, we just have a different notation for co-product. Now we have these two morphisms, but we're talking about morphisms now in C op. So what we're going to get are morphisms from A to A plus B in C, and B to A plus B in C. So we have, here we have that right here. So we have A plus B, and two morphisms like this, that you might call iota A and iota B. Okay, and then we have this property, which is going to be the same, but we just switch all the arrows around. Okay, so if we have another guy, so maybe I should say that this type of thing is called a cospan, because length span, but the arrows are not pointing inwards, they're backwards. Okay? So if we have another cospan, so imagine all the arrows are in the opposite direction. If we have another cospan coming from A and B, then we're going to get a unique arrow pointing up, making those triangles meet. So let me draw that. So if I have another cospan between A and B, then I get a unique morphism pointing up. So it's just the same definition, but I just switched all the arrows. Okay, so now my question is, what is the coproduct in set? Yeah.
Is it union?
Yeah, exactly. It's a disjoint union. So let's think about it. We have two sets, A and B. I claim that the coproduct here is the disjoint union of A and B. So we definitely have two natural inclusions, right, of different components. And if we know how to map those two different components, let's just say, to another set, D, then we can map the disjoint union to D. Okay.
What's the disjoint union?
Oh, okay. Okay.
I know what the union is, but I don't know.
I say disjoint, I don't know why, that's what people say, because I want to make it clear that I don't have any information about how A and B might overlap. Like, they're different things, and they don't have any chance of having an intersection. So just taking the against these things are like completely unrelated.
So if they have elements in common, you can still do disjoint union in system. Or are you not allowed to do a disjoint union if they have elements in common?
Let's not talk about having elements in common.
Oh,
It was kind of weird. We just have two sets.
okay.
They're just coming from different places. So they couldn't have elements in common, so they're like that.
Okay, all we can do is substitution for and then see it's clearly not this
That's a good idea, yeah. Yeah, I'm scared by the concept of non-disjoint union, because say you want to take the union, and you're kind of unclear about whether it's disjoint or it's not, the natural numbers and integers. Do you want to like identify the zero in the natural numbers and integers or not? Kind of weird. So let's find it there. We just put A and B together in two separate paths into A plus B. And if we know how to map each half into Z, then we know how to map the whole thing into Z.
Sorry, so, the indicators and disjoint measure the naturals will give you like, the integers indexed with little z, and then also all the naturals indexed with little n.
Yeah, that was the way to do it. Yes. Okay, yes.
So in, like, the problem with this correspond to like the sum type?
So what would you say first and what?
In like prop or type, I can't remember which category. Do this correspond to the sum type?
Exactly, yeah. So in the type theory that Anya presented last week, this is exactly the sum type. These two guys are in left and in right, usually it's called, in slides like that. And then the inductive principle of the co-product or the sum type in type theory is exactly the same. So, yeah, you can pattern match on A and Z, you say where they should go in Z, then you get a map. You get a function from A plus B to Z. Okay, what about prop though? Oh, yes, disjunction. So in prop, this is disjunction. So first we need, this is probably too small. Okay, let's erase this. Okay, so in prop, this is just disjunction. Because first of all, we know that if we know that A is true, then A or B is true. Also, if we know B is true, then we know A or B is true. And if I can prove Z from either the hypothesis A or the hypothesis B, then the rules, so maybe just to be concrete, we can say that we're doing like natural reduction in like an intuitionistic style, so like an intuitionistic, or in the sense that to prove, to prove the or to produce something from the or, we really need to know either A is true or B is true. So to prove Z from A or B, we need to be able to prove it just in the case that A is true, or in the case that B is true. Okay, so then we get this implication. Okay, and so now, from a categorical perspective, we can say that conjunction and disjunction are dual to each other. They're the same thing, basically, like from a very abstract perspective, they're just the opposite of each other. Okay, there's maybe something that you already kind of okay, any questions before I move on? Yeah.
Would there be a co-category for any category out there?
Is there a what category?
A co-category,
A co-category?
yeah, like a co-product.
I don't know what you mean by
So,
co-category.
It seems like the co-product category is the where you have all the numbers in inverse.
Ah, So you mean like the one of spans that I defined?
Yeah.
Yeah, exactly. So the whole story that I've told can be dualized. Everything in category theory can be dualized, and then you get another story for free. So the three definitions that I gave, and everything that I said about them, can all be dualized. So this one can be dualized, and then what it says is that Homs from A plus B into Z, so we switch the order here from A plus B into Z, are the same as Homs from A to Z and B to Z. And what else did I say? So yeah, the whole thing about the spans can also be dualized. Then we have a category of closed spans. Yeah.
So there with the operations into the joint union and sets?
No. So that's a tricky thing. It's still time.
Okay.
You have to be on the ball and know where to dualize. Because yeah, if you were just doing it naively, you think I could dualize everything. And then this should be plus. So maybe one thing to say is like, okay, I said that everything can be dualized, but just maybe a why. Because like, when we think about examples, that can't really be dualized. Like what I argued that the product and set is just a normal product and set. That doesn't really give you any information about what the co-product and set is. You still have to think about that. And here, we're like in a very specific category, set. So we want to say in that same category, we want to have the same kind of connectors, I guess, in set. We don't want to dualize the set op. We're dualizing C to C op, but not set to set op. Okay, yes.
Just an observation. What did you write on the arrows from B and A into the co-product?
Iota.
Iota, okay.
Yeah. In type theory, you would write like I and L for in left and I and R for in right. I use iota because I also use the three-letter here pi. Okay, so now I want to talk a bit more specifically about the simply type random calculus. So, let me. So let's fix a simply typed random calculus. So for simply typed lambda calculus. So I mean by A, I mean like should definitely have all the normal structural rules like weakening and stuff. But maybe it's kind of unclear what type format you have in a simply typed lambda calculus. Like maybe you have product types, maybe you have unit types, maybe you have function types. People are not that consistent, so maybe you can have other types if you want as well. So let's fix a simply typed lambda calculus T, full T. We want to define the syntactic category. We're going to call curly C of T. So now I'm basically just being more precise about the definition of this category pi that I was talking about in the previous days. So we want to define a syntactic category CT by the following. So when we define the category, we always have to define the objects. So the objects I want to say are the types that you can derive in this type theory. Maybe I'll just whisper that if you know more stuff about this, this will probably be the context. So I'm just making some simplifications here so it's not so complicated. In the end, it will be the same anyway. So let's just say that the objects are types. And the morphisms are derivable judgments of the form X and S, T and T. So if you can build up a type with all the rules of your simply typed lambda calculus that is an object of this category, and if you can derive a judgment like this, then you get a morphism in the category. And maybe I should say that the morphisms we quotient by alpha equivalence. Do you guys know what that is? So whether you use like X or Y or Z here, we don't care. So, question I have for you guys is, what is the identity in this category? What do you think of what?
Referencivity from X being type is S, you can conclude that X is type is S.
Yes, exactly. Yeah, so this rule has a million names, like variable, projection, numeric element, stuff like that. Okay, so the identity is that, can you guys do the last one here? Okay, so the identity is a judgment. You judgment is the type limit calculus, it looks like this. Because we use X here. And what about composition? Maybe I'll write down some of the data that we need for composition. So for composition, of course, we need two morphisms, and then we're going to compose them together. So if we have two morphisms, then they look like this. We have a morphism from S to T, and a morphism from T to U. So how should I get now a morphism, say, a morphism from S? And a morphism from S to U. So what should I put in the whole case?
Derivation, you go from S to T and then T to U.
Yes, but how? Yeah,
I'm gonna take a wild guess. Is it the cut rule?
yeah, definitely call the cut rule in some situations. Maybe now I would call it substitution. So we have a U in U that requires some guy in T that here is called Y. But here we have a guy in hand. I mean, we're assuming that we have something in S, so we have a guy in hand here in T. So we can substitute in the T for Y in U. Does notation make sense to everyone? Maybe using this side. So, yeah, so we can just substitute in T for Y. And now we get exactly what we want. Okay, so then maybe it's up to you to check the unitality and the associativity. Okay. So now we have a category for any simply type lambda calculus. And I want to think about product in this guy. So usually in the simply type lambda calculus, you assume that you have products. Maybe not always.